Okay, I think we're going. We are streaming. Hello, everybody. Testing. Oh yeah, look at that. Look at those volume letters, levels. Very nice. Hello, everybody. Welcome back to another catastrophe that is a deep astronomy live stream. My name is Tony Darnell, and today we're going to be talking about something I just have been thinking about, and amazingly enough, Ethan Siegel wrote about yesterday in a blog post that we're going to go through about how the universe has become even more inaccessible to us than it has been before. I mean, it's always been this way, but now we're going to talk about it, and I'm going to get us going here on the social media platforms of all of our choice. I'm streaming on Facebook and Twitter and let's see, Twitch and the YouTube and all of those places. So I should be there looking at all of your chat. So I hope you'll interact with me. The format of these streams these days, I've changed it around quite a bit, but the format of these streams is I pick a topic, and today I picked one that I think you'll find interesting about how most of the galaxies we're never, ever, ever going to get to, no matter what we try and do. 94% of the galaxies in the universe, forget about it, right? And we are going to be, so we'll chat about this. I'll give you my little spiel, my little my prepared remarks that I have in front of everything, and then we will chat about it later on the different chat networks. And if you join my Discord server, the link to that's in the description box on YouTube. It also goes through on the Twitch chat bot thing. I have a timer on there, so you can click on the invitation to get on the Deep Astronomy Discord server and go to the live stream channel, live stream voice channel. And if you have a mic, I will put on my earphones here in just a minute, and we will discuss, and I can hear you, and I'll put you in to the stream as well. So we'll be able to chat and talk about these things. Okay, so that's the format. That's what we're going to do today. But first, space news, everyone. Let me show you some really cool space things that have just come out. I talked yesterday, or actually last week. I put out another countdown to JWST where we learned that the space telescope is now in the launch port. It is there getting ready to be put on a rocket. So JWST is no longer in the States, and it is now on its next stage before reaching final outer space. It is it's in French Guiana. So that happened last week. If you have not seen the countdown to JWST episode, please go over and do that. I posted it on YouTube and Facebook, and so please go check it out. And I'll post it on Twitter here a little bit later. And so that happened. Also, a couple of weeks ago, maybe it was last week. We did a stream on the Lucy spacecraft, and it is going to the so-called Trojan asteroids, where we learned about what those were near Jupiter. It's on its way, but after it launched last week, early Saturday morning, they went to go deploy the solar array, and one of the little clickety ratchety things that was supposed to clickety ratchet didn't clickety ratchet, and so while the solar panel or solar array is deployed, NASA's a little bit worried because it didn't clickety latch into place. So it should work okay, but that happened, and NASA's a little bit nervous about it. These solar arrays are 18 kilowatts total when they're near the Earth. So that's a lot of electricity going through those while it's close to the sun. But when it gets to Jupiter, that's going to drop down to 500 watts. So these solar arrays are vital to the success of the mission. And so the little clickety latch thing is a bit of a problem. So that is also, so the launch happened. NASA doesn't expect anything, it doesn't affect the health of the mission. It doesn't affect the future prospects of getting the data and the scientific mission that it's on. So everything's okay as far as that goes. But they kind of wish the clickety latch would have happened, is what they're saying. And then just today, I was reading in my news feed. Sorry, this is on space.com, so we got to deal with a lot of bullshit advertising. And here's Best Buy. So if you need a stove, this is an algorithm fail, because I I don't need anything from Best Buy. How come it doesn't know this? This is an algorithm fail we're looking at here, folks. But anyway, Europe has a gamma ray telescope up in space, has had one since 2002, and it's called the Integral spacecraft, and it experienced what I experience every day, a single event upset. Now, a single event upset occurs when a charged particle, like a cosmic ray or a gamma ray of some kind, hits a piece of electronic equipment that happens to be pretty important on the spacecraft. It experienced one of those late last month and sent it into a bit which caused one of the three reaction wheels. This is the thing that keeps it stable and pointing in space, to stop. And so the spacecraft started tumbling. And they noticed this because the data coming back were kind of weird, right? It was kind of coming back in chunks and they were losing power. So that means the solar arrays weren't pointed where they were supposed to be pointed to. So they they looked around and see what it was, and turned some stuff off and back on again, which is what everybody does when they first start to troubleshoot things. And it started to regain more control of the spacecraft, and now everything is fine. Integral has been one of those spacecraft. We worry about JWST going up, but Integral has been one of those spacecraft that has been up for a very, very long time with no repairs. Another spacecraft that this has been true for has been SOHO. It's been up since 95. So we've got plenty of experience with spacecraft being up in space, doing things with no repairs whatsoever. Chandra is another good example. Been up there for decades. And so this is a good sign that we have all these telescopes that have been up there for so long without needing any repair. So I'm not so worried about JWST. I say that, but I really am. Especially after it deploys. Once it deploys, I'll feel like, phew, okay, everything's going to be fine. That thing doesn't deploy, all manner of things are going to be a problem. So that there's a little bit of space news, things that passed my eye over the last few days. So I thought I'd share those with you. Today, I want to talk about the universe. It's getting a little bit personal with me because, let me just show you here. See if I can find this. Here we go. Here is the state of affairs we find ourselves in. Let me embiggen this. Can you see this? This is the universe as we currently understand it. 68% of it is dark energy. 27% of it is dark matter. And that little slice right here, 5 or 6% or so, right here, this little slice of pie, as Carl Sagan would say, that's us. All the humans that have ever been born, all of the atoms that make up all the people in the history of all of humanity, all of the planets and the stars, all of the things that shine, everything that we can touch, taste, feel, smell, cook, kill, massage, everything is in this tiny slice of pie. That's us. That's everything. That's all that we can interact with. 95% of everything else in this universe won't have anything to do with us. Now, it's hard not to take that personally. And this all came about because of this annoying thing that the universe is doing, which is expanding and accelerating as it does so. Today, I'm going to go through an article that was written by one of my favorite science communicators, Ethan Siegel. If you don't know who that is, he's a blogger, and he goes by the handle Starts with a Bang. And he was writing for Forbes.com for a really, really long time. He probably still is, but that went behind a paywall. So I haven't read his stuff in quite a while. But then lately, I've been seeing his stuff on this website called Big Think. So I guess he's syndicating his stuff now. Anyway, really good science communicator. I love the way he writes. So if you need somebody to help you understand some of this stuff, I heartily recommend him. He's right there with some of my other favorite science communicators. Sean Carroll from Caltech. He's one of the best you're ever going to see for spoken word. And so I would definitely highly recommend him if you don't know about him yet. And of course, there's all the others that you know about too. I have my favorites, but those are two that I would highly recommend. So today, let me pull this thing up. Here is his headline. This was from yesterday. 94% of the universe's galaxies are permanently beyond our reach. Now, we didn't know until just recently that the universe was accelerating as it expands. And this is a crucial component of this statement here. But when we look out in the universe, by the way, every Monday, what he does is this thing called Mostly Mute Mondays, where he tells us a story using primarily just pictures, which is great for me because I don't need to worry about making slides. I'm just going to scroll through this and we're going to talk about the various aspects of it as we go along. So, I mean, the universe. Here's an image of distant galaxies, all very very far away, and when we look up and we see these, we can see that galaxies are more or less isotropic across the galaxy, across the universe. Everywhere we look with a telescope looks more or less like this. We see a smattering of galaxies filling the viewport of the telescope that we're using, and we're seeing all these distant galaxies. So, and the universe, and I've said this, I've said this in many different contexts, but right now, as we understand it, the visible universe has about 2 trillion galaxies in it. And again, this is more or less what they look like, right? This is a really nice rendering of the Hubble Deep Field or the Extreme Deep Field that was exposed for 23 days. And in the background, the Hubble Ultra Deep Field, which was taken in the early 2000s, and they exposed Hubble for 11 days. And you can see there's about an equal distribution of galaxies in both of these images. Every single dot in there, by the way, is a galaxy. Some of them are very far away. And we measure their redshifts. They look very irregular. They are very strange looking galaxies, especially the most distant from us. And so here's a very simple animated GIF of what's going on with the expanding universe. I use this in an old video of mine, where there's just two galaxies expanding away from each other, and the wavelength from one galaxy travels to the other galaxy and is redshifted as it finally arrives at the distant galaxy, or at the uh, home galaxy. Pretty simple concept, but it has a lot of ramifications. And so what Ethan said in this article is anything beyond about 14.5 billion light years away from us, any galaxy that is 14 or so billion light years away, we can't get there because the expansion rate of the galaxies at that distance is faster than the speed of light. And that may seem counterintuitive, but this was a topic that I had brought up in another video that I made many, many years ago called, how can galaxies go faster than the speed of light? I made a comment in one of my first videos ever that when you look at the redshifts of these galaxies from very far away, some of them have redshifts that are so great that they appear to be moving faster than the speed of light. How can that be? Well, the reason, as I mansplained to you, is that the universe, while the speed of light and most things in the universe are constrained by Einstein's theory of relativity, which does not permit things traveling faster than light, it does not that says nothing about the rate at which space-time itself can expand. So space-time can get bigger all the time. In fact, it is getting faster and faster as it accelerates in its expansion, and it's not limited by the speed of light limit. So it can go much, much faster. And it is at the point of about 14 billion light years or so, when things are about that far away, that the expansion rate gets to the point where we could never catch it. Even if we left today to some of these galaxies, say 15 billion light years away, we would never be able to reach it, even if we left at the speed of light. So that means that all of those galaxies, a full 96% of them, in we can never get to. We're cut off from because of the speed of light limit. Now, the universe itself, this is a little. The universe itself is about, not about. It's taking all this into account. The universe is about 93 billion light years across, 46 or so billion light years radius. And this would be our observable universe. This is the size of it right now. And of course, that's expanding. And the galaxies that are inside the observable universe are accelerating out past the boundary of the observable universe. And that boundary, this boundary, this big white circle here, is the any objects that are at that limit of 46 billion light years away. The light that left those objects would only just now be able to reach us in a universe that's 13 billion years old. So that's what defines the limit of the observable universe. And right now, it's about 93 billion light years. As the universe gets older, that increases. So as I was just saying, the universe is also accelerating. And here's 4 possibilities. This is taken from Ethan's book called Beyond the Galaxy, which I haven't read, but it's on my list. We have 4 different possible ways the universe could be. The universe could be closed and decelerating. And this first top thing is what astronomers were very sure was the case before they did their Type 1a supernova work that it resulted in Nobel Prizes for Adam Rees and Perlmutter and all those other guys. They thought, they were so sure that it was going to be they were going to find a decelerating universe. They called their study that, measuring the deceleration of the universe. Not only did they not find that, they found this bottom thing, right, where the universe was flat but accelerating and getting larger and larger with time, getting faster and faster with time. And the interesting thing about this is implying, this bottom panel here, that there is a force pushing the universe apart or accelerating, causing space-time to grow, causing it to get bigger. Now, we don't know anything else about dark energy but that one thing, but and this other very crucial fact, which is that no matter how big the universe gets, the amount of dark energy in it stays constant. And that's down here in this panel here. Here's what an expanding universe looks like. This top row, pretty much common sense. As the universe gets bigger, the matter within it gets more diffuse. The radiation, same thing. That's this middle panel. And you can see on this right side the different graphs that show what that decay rate would be. But the energy density of the space-time itself, this is a component of space-time itself, stays the same. No matter how big the universe gets, there's the same amount of dark energy in it. And that is really a counterintuitive thought. It's inherent in the nature of space-time itself that the amount of dark energy within the universe stays the same. So matter goes down, gets more diffuse. Energy goes down, gets more diffuse. But the amount of dark energy stays the same. Okay, so here's a pretty good graphic of how far back we can see with our current galaxy surveys. We have this area between where the Sloan Digital Sky Survey is data here and the intergalactic gap and the gas and the dark ages. There's galaxies in here, and JWST is going to be able to show us this region of the universe. Right now, we're kind of limited. Hubble can see back. Let's see where I looked this up. What was the most? Here's the most distant galaxy. It's called GNZ 11, and it was seen back when 13.4 billion years in the past. So Hubble observed this back in 2016. It's not a very remarkable galaxy. There's a picture of it there. And you can see in another representation what I just showed you, this area of reionization, and the very first stars and galaxies are going to be in this region here, where JWST is going to look. First stars, first galaxies, and right now this is what Hubble can see right now as the farthest galaxy that we've got. We can never reach this galaxy. Okay, the most we can get to, if it's too far away. And by the time if we left now and went at the speed of light, we could never hope to reach that galaxy at all. And here's another representation of the observable universe, which is this yellow circle, and the pink circle within it is what we could get to if we could travel at the speed of light. So all of the stuff between the pink and the yellow, we're not getting to. But if it's less than about 18 billion light years away, we could get to it if we went travel at the speed of light. And here's what's going on. This is why. So in this top panel, this is broken up into A, B, and C, and this is made by some guys in Calgary, which are pretty good with has pretty good cosmology information in it. But if we have a galaxy here in this circle called Galaxy A, and it is roughly 13 or so billion years away from us when it emits this light. Here is a spectrum of what it would look like. In the yellow, you can see the two. He just drew two spectral lines. There's a lot more in a galaxy, but you can see from these two spectral lines where the galaxy is. Time goes by. Oh, and the only motion that's going on here is the local motion of the galaxy. But some time goes by, a few billion years. Well, the universe expands, pushing the galaxy even further out. And so now the galaxy is redshifted more into the red. And finally, we get to a point, present day, when Earth is now in existence. Back here, there is no Earth. Earth is just being formed in the early part of the solar system, about 5 billion years ago. Now Earth is here. The light finally arrives. It's been redshifted well into the red, but the expansion of the universe has happened so far that now the actual distance of this thing is well over 80 light years, right? So it's really far away, and we can't even hope to get to it over the course of so. In addition to the redshift, the expansion rate of the universe is making these galaxies get further and further out of our reach at every moment. In fact, every year, 160 billion stars, which is enough to basically compose one major galaxy, become newly unreachable. They pass that point of the observable universe. And the final galaxies that we'll be able to get to are the one in the M81 group, and they're going to become unreachable. They're going to reach that point in 100 billion years, and then we're going to be just left with the galaxies in our local group. And I like this one better. This was taken from Wikipedia. You can see the Milky Way galaxy right down here. There's various things within the Milky Way galaxy labeled here: Carina, the Sextans, Coma Cluster, things like that. But up here is M31, M33, and then also a little bit further away are nearby galaxies outside of the local group. So here's our local group, and these are nearby galaxies just outside of it. These are not expanding away from us due to expansion rate of the universe. In fact, M31, as many of you already know, is heading right this way. So the Milky Way and M31 are on a collision course. So the large scale expansion of the universe, well over 2.5 million light years, is causing the other galaxies to expand away, but not the local group. Okay, so that is pretty cool. I mean, if you like an antisocial universe, and people always accuse me when I talk about life in the universe of being putting humans on some kind of special place, because I actually think, or I think it's very plausible that we are the only civilization, not only in the galaxy, but in the entire universe. And I think that's plausible. But if life is common, or I'm sorry, if life is rare in the galaxy, then the civilizations are even rarer. And if we look for other civilizations, we're going to have to look within our own galaxy because most of them are gone now. We can only see around 6%, or even hope to get to 6% of the galaxies in our universe. I misspoke. They're not cut off from us. We can still see them, but we could never get to them. And that's different. If they're over 18 billion light years away, we could conceivably, if we could travel at the speed of light, get there. But we can, but if they're greater than that, we could never get there, but we could still see them. So between 18 and 47 or 46 billion light years away, we can still see them. It's only when they pass the observable universe at 46 billion light years that we can't see them anymore. So the universe, turns out, as big as it is pretty darn elusive. So what are we going to do about this? I don't know, but I find that this is a little bit hard to take. Not really, I'm just kidding. From a personal perspective, I mean, we just don't have a lot of interaction with the universe. That little 4 or 5% slice that we interact with is actually tiny compared to what's out there. So that's my spiel. It took about as long as I had hoped. Let me get to some of your content. Let me just put in my earphones here and let's see if anybody is in the thing. All right. Nope. No, it's okay. Yeah, Peter's in there. So let's see, Peter's in there, and that's it. Where? Make sure. There, put that on. Okay. All right. So let me read some of the comments here. If you guys want to join the Discord server, please do. If you want something you want to add, by all means. So I'm just going to start. I don't have Discord muted. You're not muted, Peter. You must have muted yourself. So Kenneth is commenting. The galaxies are not moving through space. They are moving in space because space is also moving. In other words, the universe has no center. Everything is moving away from everything else. That's right. The galaxies do have a proper motion, but we only see that proper motion at small scales, like within our own local group. What we see from our vantage point is the large scale expansion of the universe itself. And that is not too unlike a sheet that is being pulled constantly. No matter where you stand on that sheet, everything else is going away from you at the same rate, or actually it's accelerating now as it does so. But every galaxy from our vantage point appears to be moving away because of that. And it would be true if you were in any other galaxy. They would also appear to be moving away from that galaxy wherever you happen to be. The point that I hope I made, and that Ethan made a hell of a lot better than I did, which was that there is a point beyond which a galaxy can exist that we can never ever reach, even if we traveled at the fastest possible speed. So if we were to somehow leave the Earth and this galaxy at the speed of light and head off to a galaxy that was 15 billion light years or 19 billion light years away, we wouldn't make it. We would never get there because it would be expanding faster and faster away from us at a point that we would never catch it. And that point, that where the expansion rate of the universe appears to be faster than light, is at the 18 million or 18 billion light year mark.
At the speed of light, and that galaxy traveling at the speed of light as well, and you could only see that, it would seem like you were just standing still, because you're not gaining up any ground on it.
Um, if it well, no, it's going to recede away from you because it's going faster than you can
Yeah,
possibly hope to go.
but I'm just so if it's going faster, it'll look like it's going further and further away.
Hmm.
But if you're at the same speed, it'll feel like you're just standing still.
Yeah. Okay, let me get to Julia. Which side of the cosmological expansion speed debate are you on? Standard candles, CMB, etc. So Julia's talking about this disagreement between the expansion rate of the universe. Two different independent methods of expanding or of measuring the expansion rate of the universe have come up with different answers. I don't have the numbers off the top of my head. One was like 76 megaparsecs uh, per something. I forget the units now of the Hubble constant, but there were two. The point is they were two different numbers, and the numbers were outside of the error bars of both of those measurements. So both people thought they had the right answer to within a certain estimate, and they don't overlap, which means somebody is wrong. Which one is the right one? So it's called the cosmological crisis or something like that, I think. And I don't know. You asked my opinion. Which side of the debate am I on? I guess if I had to pick a side, I would be more in line with the CMB guys, just because I am questioning our assumptions about what we are calling standard candles, and there could be
Mm.
something about Type 1A supernovae that we don't fully understand. Right now, the way it works is when you look at a Type 1A supernova, these are very specific kinds of supernovae that blow up when a white dwarf has sucked up enough material to explode off of a companion, and the light curve from that explosion is a is related by a function to distance, and so they call that a standard candle. And because if they see this curve, they see the peak, and they can tell how far away something is intrinsically. And when you know how far away something is intrinsically, you know, or I'm sorry, when you know how bright something is intrinsically, then you know how far away it is by using the inverse square law.
Yeah.
So I think this is just me thinking, which I should never really do, but I do anyway. And it's that I think we've got some problems there. Same with Cepheid variables. I wonder if we don't, if we're not a little bit misled about some of the Cepheid variable um, science that's going on. I don't. I mean, this is the stuff that led to Hubble seeing, the expansion rate at all. So it's important, and I think there's something there that's right. But I mean, I do think they can be good standard candles, but maybe our calibration is a little off. That's my thinking on this. So let's see. Anthroparian. It's a good thing there are astronomers around now recording images, as if it was a few billions later in the future. We probably could have discovered everything with our only our eyeballs. Um, yeah, that's very true.
Yep.
All right. Another comment. If scientists said Andromeda Galaxy and Milky Way are collapsing, how do you explain the universe expanding? They're not collapsing, they're colliding. And again, like I said, the expansion rate of the universe is a large scale phenomenon. So if you are uh, you can have swarms of galaxies close by
Yeah.
each other,
Like
and they would be
like our
going
local
towards each
group.
other, and they would be some of them would be appearing to go towards each other, or maybe even close or slightly away. Uh, that's local. That is relatively nearby. Those galaxies are gravitationally bound. That's what they are connected by their gravity. For really large scale things that are well outside of that, the effect of cosmic acceleration takes over. And so all of space time is getting bigger in between these galaxy clusters. And while it is possible that within a local group they could eventually begin to expand, they'd have to drift apart quite a bit for that to really
Hmm.
be a noticeable effect. All expansion, acceleration, the universal expansion effects are felt at very large scales, are seen at very large scales. If they're gravitationally bound, then this effect isn't dominant. Um, all right, E-Bone. It seems there are several types of type 1A. So yes, there are, and I think they're learning more about this all the time. So um, I think the problem may be there. Um, and Sean, let's see what Sean says. With the universe expanding, do we know at what point galaxies must travel away from us versus be able to travel towards us, like, for example, Andromeda? Um, well, like I just said, I don't know if there's like a clear, I guess if anything, it would be this idea of being gravitationally bound. And that would be like the moon around the Earth. The moon is gravitationally bound to the Earth. The Earth is gravitationally bound to the sun. All the planets are gravitationally bound to the sun. So at the point at which an object is not gravitationally bound, right now I think Andromeda and Milky Way are. And certainly their trajectories are such that the expansion rate of the universe isn't going to be enough to push them away right anytime soon, I think. So I think that's the limiting thing, but I don't know for sure if that's true. And also I don't know at what point, and it would vary depending on what it is, right? Two galaxies gravitationally bound would be a hell of a lot farther apart from each other than a planet gravitationally bound to a star. So, these effects are different depending on the type of object we're talking about. This also doesn't happen with atoms. So the atoms in your body, the space-time in between the atoms in your body isn't causing your body to inflate, right? These are completely different forces are in charge at that scale, right? You have these
I thought eventually that the atoms would fly apart.
not in your body. No, there's way too many.
Well,
There's way
we'll all be dead by then anyway.
well. If you're talking about just randomly floating, interstellar medium kind of stuff, that's different.
Yeah,
I'm talking about the stuff that makes up solid matter and everything else. Those are bound.
yeah, because those atoms are bound like the planet is to the star.
Well, they're bound with different forces. So
Yeah,
the electromagnetic or the what is it called? The weak and the strong forces are in charge in that area, and that is
yeah.
not that's easily overcoming any increased space
Uh-huh.
time expansion that's going on in your body, which
Yeah,
wouldn't be
but if
very
you've got
much.
two separate atoms, they will expand away from each other. In old Jonas of time, and everything will get expanded apart,
Hey, Uncle Bill, it's good to
according
see
to
you.
the theory.
Which region? Let me just get to some questions here. Which region will Vera Rubin telescope be looking in? The whole entire sky. So Vera Rubin will be. It used to be called the LSST. It will be taking pictures of the entire night sky several times a week. Okay, so it will be looking in all the regions. It's called a survey telescope for that reason. So let's see. AP. There could have been several Big Bangs at different times after the initial bang. Could there have been several Big Bangs at different times after the initial bang that has caused the expansion? Hello from Lyon, France. Well, hello there, AP.
Bonjour.
Yeah, Jordy saying bonjour.
I've
uh,
been saying bonjour today and yesterday.
um, so the way I understand, let me answer your question. The way I understand this is, as Sean Carroll and others have explained, that we have a pretty good idea of the history of the universe all the way back to about 1 second after the Big Bang. That 1 second is pretty interesting, but we have a pretty good sense of what happened in the universe all the way back to 1 second. So unless those big bangs that you're talking about occurred within that 1 second, which I think is still open for debate. In fact, I think everything is open for debate at that point.
Yeah.
Then perhaps then that could have happened. Otherwise, there's no evidence of several other big bangs. One thing that we would very much like to learn about dark energy, especially, is whether or not it's the same everywhere. Now, as I showed you in this graph from Ethan, that the amount of dark energy in the universe is constant, regardless of how big it is. So the bigger it gets, more of it is put into it to maintain a constant level. That's hugely important to see the acceleration. But what we don't know is it the same everywhere? In other words, is the amount of dark energy in one part of the universe greater or less than the amount of dark energy in another part of the universe? That would make for some really weird observations. We would see certain parts of the universe expanding at different rates than others. Now, this could all be happening well outside the boundary of the observable universe, and we'd never know. But it stands to reason that within a 46 billion light year radius, it should also happen within that as well. And that would be a huge question that people would like answered by telescopes like the Vera Rubin telescope, because they're going to be able to characterize, they're going to be able to measure structures in the universe that cover the entire sky. And these would be, cosmic web kind of structures, tendrils of galaxies and things like that. Now, it's going to take a while to build that up, because one of the things Vera Rubin is doing is looking at large areas of the sky really quickly. It's not looking at super long 11-day exposures like what we saw with the Hubble Deep Field. It's looking at, I guess, minute-long exposures, and then they're adding them all up. So to build up a scale of images that goes that far back so that we can see very dim galaxies would take a while. But it could be done. And that might lead to clues into the nature of dark energy on a large scale. Other places like the Dark Energy Survey also try to do that. So that's a good question, though. Hello, Raj. It's good to see you. What did he mean by a flat universe? Well, just that, a flat universe, right? The geometry, it's not like,
Yeah.
curved or open or anything else. I mean, literally, you take three things out in LISA is a good example. The proposed LISA space antenna, right? It's going to have three nodes placed 50,000 kilometers apart. And if we lived in a closed universe, a curved universe, then the points of that triangle would not add up to 180 degrees. But in a flat universe, they would all add up. It's just geometry. So that's what it means. Flat. It's not curved in any weird way. As it expands, it's all more or less like a flat sheet built up in 3 dimensions. That's what they mean by flat universe. It's really that.
Yeah,
It's
it's
really
not
that simple.
wibbly wobbly, but it is timey-wimey.
Yes, that's right. And
Doctor Who
Ebone,
speak.
Einstein said that nothing can travel faster than the speed of light in space, but space itself can. That's right. Space isn't limited by this expansion speed limit or by this cosmic
No.
speed limit. So, yay, we are back in the middle of it again. Yes, we're back in the middle of the universe. Isn't it great how we always end up back here? And Galaxy also recommends Ethan Siegel. So,
Yeah.
yeah, he has a podcast, and of course his here's what I think. I really here are my favorite science communicators, right? So Ethan is a good writer. I like him. I also like Avi Loeb. I think Avi Loeb from Harvard does a really good. His books are very thoughtful and very well written. Sean Carroll, of course, is my favorite when it comes to speaking. He can give a
Yeah.
talk and really understand really well what he's getting at. And he gave a great courses way back in the mid 2000s where he talked about dark matter and dark energy. If you want a really good introduction into those concepts, watch his great courses lectures from like 2006, I think they were. Absolutely pristine, perfect explanations of what's going on. I still to this day refer to them in when I write scripts and talk about these topics. So Sean Carroll's really big. And then I like, I guess, to get away from the white guys for a minute, I also like Physics Girl on YouTube. She does a really good job. And of course, Hank Green does a good job, back to the white guys. But I love the way Hank Green talks. He talks with very specific ways of going. He says his words like this, and he chops up his words, and then he gets higher in his talking, and then he gets lower in his talking, and then he does like this. And it's very easy to follow Hank Green. So I love Hank Green. And let's see. Of course, the biggies. You got to talk about NDT. NDT is pretty good. He's been around forever. Neil deGrasse Tyson and his buddy, his buddy Bill Nye. Bill Nye reminds me of the Kim Kardashian of science communicators. He's just glad to be there.
Yeah.
He wants to be famous, right? He just wants to be famous. So
Mhm.
so he's kind of like the Kim Kardashian of the science communicators, I think. So those are some of my favorites. And of course, I was going to end I forgot to talk about this in the end, but of course, one of my all-time favorites is Brian Cox, sorry, from the
Yeah.
BBC. And
From
I saw,
Daydream.
yeah, and that's right. He's got a new BBC show out called Universe.
Daydream.
And what I like about Brian Greene, I just saw this, and he came up. This was I think his article just came out today. But Earth's demise could rid the galaxy of meaning. And he warns ahead of COP6. COP26 is this global climate conference that's coming up,
Yeah.
and he makes a statement in here where he says what we've discovered is I think it's a reasonable working assumption is that there are very few civilizations per galaxy. And if that's true, and I happen to agree with that, and of course, what we've just learned is that there's even now fewer that'll ever be available to us because of this expanding universe thing. So 96% of any galaxies that have any civilizations in them aren't going to be available to us. Um, but he's making this point that if we don't do something with climate change, and we are snuffed out as a result of it, then the galaxy of which there is only one technological civilization, if that's true, would lose a sense of meaning. Now, say what you will about that. That's a little bit over the top, I think. But I don't know. At least he's trying. I like Brian Cox because he's low key
Mhm.
and he's very easy to follow. But of course, the master, the communicator to rule them all is David Attenborough. So I'm just
Yeah.
hands down the all-time favorite. Sir David Attenborough is the best all-time communicator, in my opinion. I don't know why I went off on that, but um, there you go. So Ethan Siegel does a great job, and there's all the others I like as well. So, all right. Greetings from Gibraltar. Hey, you know who we haven't heard from in a long time is oh boy, what
Yes, Andrew Planet. No,
yeah,
he
Andrew
was here
Planet.
last
Yeah,
year.
Andrew Planet
Yeah.
hasn't been here in a long time. He's
Yeah.
from Gibraltar. He's been probably very busy. Um, but anyway, welcome. It's good to have you here. Um, Dennis Van Der This is from Twitch, I think. Until some slides over here to our dimension, still disproven to me, but I am a believer. You talking about life? Okay.
And Brian Keating has a point as well about SETI.
What's his point?
Maybe it's time to stop the funding to SETI or change it. Stop the funding and set up a new search. But the
I didn't know he
search
said that.
for extraterrestrial life, because we're hitting a bit of a big zero with SETI. But
Does
I
he really
think
say that?
life
He really
may be
says
the
that?
way to go.
Huh, that doesn't sound like him. Well, I don't agree. I think we should keep looking. That seems like, I mean,
Well, yes, but
it costs
it'll
very little to
incorporate
keep
SETI
going.
as well.
What?
This is what Brian's been saying, that it would incorporate parts of SETI.
What would incorporate parts?
Because if you're looking for aliens of any sort, you would also be looking for the intelligent ones as well at the same time. Make it more general and more catch-all
Well,
than just
well,
intelligence.
that's sort of okay. So what we're doing now with SETI, as I understand it, is we've got all of these. We got the Allen array of telescopes, your radio telescopes. They're installed up in California, and they're looking at millions of wavelengths all at once in the radio, in the hope of detecting some artificial signal, one that doesn't emanate from a naturally occurring object like a star,
Yeah.
a pulsar, things like that. Well, that's implied in that they're looking for intelligent aliens. So
Yeah.
that's already worked into the SETI plan. So to cut that off means that we're not looking for alien life at all.
Well,
and I disagree with that. I think we should at
it
least keep listening. I see
it's
nothing wrong with
just
that.
changing the name, really,
Changing the
and
name.
then expand on it.
Well, expanding, yeah, but that's different than canceling it. You said cancel.
Well, cancel and set up something new.
Oh,
Well, it's basically the same as expanding on SETI.
okay. Well, I think that's fine. I don't see anything wrong with that.
Yeah,
I heard you say
so we can
cancel,
look
and I
for
think
life
that
at the same time, the biological processes.
okay. Well, sure. I guess I can get behind that.
Yeah.
Jim and Boo. I'd be happy if JWST can at least detect a Dyson sphere. Yes, of course. That would be
Yes, we
nice.
can.
That would be great. Um,
Tabby Star, for example, was a
hadn't factored in.
possibility,
Yeah.
but
Did
it
you
was ruled out.
did you like my Carl Sagan impression? That's us.
Uh,
Human being, all of us, every person that's ever had an atom is there.
yes.
For as long as humans have had atoms, we have forever lived in this 4% slice of the pie. It's terrible. Are you kidding? Oh my gosh. Okay. Any new comments? Let me look. Otherwise I'm gonna head out. Let's see.
Well,
Uh,
we do have a first-time chatter on Twitch who is asking about an episode on instrumentation.
of what? Of JWST?
On the Vera Rubin, I think. I believe it. Yeah.
Oh, the instrumentation on Vera Rubin.
2040. Yeah.
Well, we could do
Or
that. You know
maybe
what? I tell you what. I will do a stream on that either this Thursday or next Tuesday. Here's what I'm thinking. On Thursday, I was thinking about doing the climate effects of space exploration. How many tons
yes,
of
rockets.
CO2 does a rocket launch put out, whether it's
Yeah.
SpaceX or Blue Origin or whatever, and then see what kind of effect that has on global warming. I was going to do that, not global warming, climate change, or I could do this. I could talk about the Vera Rubin Space Telescope. Can I put? I don't know how to put in a vote thingy. There's a way to put in
The
votes.
thing with the
You tell me what you want in the
launch,
chat.
the thing with the Chattanooga launch was afterwards, they all basically ignored him, tried to get to the champagne when he was trying to articulate what he experienced.
Yeah, I heard that. He cut him off.
Yeah.
Yeah.
It looks like that overview effect has affected him.
Yeah, well, I
You
guess,
know.
yeah, I've heard about that. Well, I get, yeah, I mean, I
And he's
can't
been
speak. I saw
discussing it
that.
on Twitter.
I don't, yeah. So,
Yeah,
Jeff
he
Bezos
has
is a
been
douchebag.
discussing it.
Not much of a surprise there.
Yeah.
All right, let me get to this comment here from Julia. Talking about actually going anywhere, should we be investing in Newman probes to scout stuff ahead of us in the solar system? The Voyagers have more than proved the value of long-term missions. Yeah, man, I think that's absolutely worth doing. These
Yeah.
are von Neumann probes, for those of you who don't know, are self-replicating probes. They use the natural resources of whatever they happen to find to build more of themselves. So this is really long-term, right? So let's say we get to, I don't know, some percent of this. They could be small, get to some percent of the speed of light, 20% or whatever it is, and get to the speed of light. They could get to some of the nearest 100 stars within a few 10,000 years.
Well, it would
and
get
and
Alpha Centauri within 16.
but not so that's just the nearest. There's other stars around there. So
Yeah.
we're looking, and they would have to replicate themselves on the way using whatever materials they find and keep going out. And I think that's a great way to go. I think we should definitely do it. But boy, do we have to have a long-term view in mind, right? We're going to have to set it and forget it, because Voyager 1 and 2, which are the fastest moving probes we've got right now, are nowhere near fast enough. They don't have any percentage of the speed of light. So
isn't New Horizons faster?
Yeah, but it doesn't matter, because
it's trailing behind.
Yeah.
But it will catch up to the point that they've gotten to.
Yeah, I don't know.
A lot quicker.
Michio Kaku. Ebowen says wants
Another
to
good
scare the
science
hell out of all
communicator.
of us. Yeah.
Yeah.
So he's been doing that since 2012. Remember back when the solar flares were all going to put us back in the agrarian days,
Yep.
and the Mayan calendar was ending, and all of that stuff was happening all at the same time. He was right up there on Fox News, proposing doom and gloom. I will say this though, the chance of a solar storm hitting us and the prospect of a solar storm hitting us is real, and it could be catastrophic. What I
Yeah.
disagree with him on is that we're going to suddenly forget how we do everything we've ever done before and not rebuild. It won't be
Yeah.
so catastrophic that we can't rebuild, but it will be a global effect, especially given how weak our electrical grids are,
Hmm.
and how unprepared we are for one of these things to happen. So it will be catastrophic. I don't want to paint a picture that it won't be, but it won't be quite so bad that we're going back to agrarian days, which is the picture he was painting back in 2012. And you're right, he does tend to want to be a little bit on the gloomy and doomy side, but in many ways, um, in some ways, he's right. But it depends on what he's talking about.
I just think with the solar flare, putting out the electric and the internet, we all of us would be looking at the skies because of the aurora. Well, the majority of where I'm not sure how far down it would go,
Yeah, that's right. We'd have a lot of
but
aurora.
a really big one could encompass the Earth.
Yep, that's
So
true.
you know,
Yeah.
I mean, there is that. There is the spectacle of the aurora.
Yeah, you're quite the optimist, Peter.
It,
Um,
it beautiful.
I've gone all Greta on you. That's right, Jimmy D. Welcome, by the way, from Australia. I'm glad you got up
Well,
in time.
no, David Attenborough's along the same lines.
Yeah, but I
He
have.
says, right, we need to start doing something right now
Yeah, yeah. I know. And
before he dies.
yeah, well, he's right.
Hopefully, well
But
before.
you know what? What kind of bugs me about him, which isn't much, but this does. He took a while to get on this train. So, but he's here now
Yeah.
finally, and
Oh, yeah.
talking about
Well, he's
biodiversity
always
and things
been
like that.
talking to it, but he hasn't
No, he
actually
hasn't. Not really.
said
He
it.
always avoided
Yeah.
the topic quite a bit in a lot of
Actually,
his specials and stuff. So
actually saying it.
yeah, that's right. So yeah. Let's see. I could put a poll on my YouTube community YouTube thing. Yeah, I don't want to do that. I don't know. So I'll just decide on Thursday. I'll tell you what. Let's just go ahead and talk about Vera Rubin. I'm better prepared to talk about that than I am the climate effects of space exploration. Anyway, I got to
Yeah.
prepare for that. So let me do that the week after. Oh wait, no, yeah, I'll have time the week after. A little bit of a preview and then I got to go. AAS got back in contact with me. Looks like we got some hangouts planned for the November and December timeframe. So we'll have some guests coming up. To talk about various things. We're working out those details now. So look for those. In the meantime, you get to participate in the disaster that is me streaming by myself. Um, so uh, anyway, you get to a couple more comments, then I'll head out. Michio Kaku has been saying for 30 years that string theory is just around the corner. You know why? Because he's a string theorist and he wants to be relevant. He's like the Kim Kardashian of scientists. Sorry, I'm picking on Kim Kardashian today. I don't know. But he just wants to be noticed. Notice string theory. Notice string theory. Yeah, we got your string theory. All right, we get it. Yeah, you love string theory. Same with Leonard Susskind. He's a big landscape kind of guy. It's CD here. It's talking about a Carrington event. That's right. The Carrington event
Yeah.
was in 18 something. It was a solar storm that
70,
had it hit.
70s.
Yeah, something like that. It was the mid 19th century. If it had
Oh,
hit today, would have wiped out most communications and electronics on the planet. So that's what they mean by a Carrington event.
1859,
At
September 1st.
Oh, isn't Google great?
There you
Uh,
go. Yeah,
about
quickly.
communicators, I like Sabine a lot. Sabine, her extreme skepticism is more than welcome as a
Sabine.
counterpoint to more
All
out
right.
there minds on the scene. Oh, I have to check that out, Julia. Thanks for letting me know. Um, and there's always Anton with his paper review show. Basing science communication in actual papers is a pretty good way to go. Have you thought about doing this with astronomy? Yeah, I mean, I did this with Space Fan News for many years. I don't know if you know about that. I did Space Fan News from 2010 until about 2018
Yeah.
or something like that. I did it for about 8
Over 10
years,
years ago.
and yeah, it was a lot of work. It's about 6 hours of work for me to put together a Space Fan News episode. I'm getting ready to start back up again. I told you guys I would start it back up in October. Basically, I do that. I pick a paper and talk about something interesting in a Space Fan News kind of way. It's a little bit different format than what Anton does. And Anton has since just exploded, right? I mean, he's
Yeah.
like a million or so subscribers and gets hundreds of thousands of views. So whatever I did would be very tiny compared to that. But yeah, I've talked about it. I'll think about it. But I don't know. I kind of like these streams. Yeah, I kind of like taking these
Yeah.
streams and just yammering for an hour and have it be kind of unscripted. More well, it's not totally unscripted, but it mostly is.
Mhm.
And it's with except for some very cringy moments, of which we have many on these streams. I don't know. I like doing these better. What I'm thinking of doing is downloading these, cutting them up into things, but that takes work. I gotta freaking start editing and
Yeah.
posting them back up again, and I don't know. Hey, it's Christian. How you doing, Christian? Welcome. Yeah, you're late because I'm getting ready to get out of
Hey,
here.
Christian.
Yeah, I'm getting ready. I'm ready to go. Getting ready. Jimmy D's here, and we gotta get Zoran. Jimmy D. Gotta get Zoran back. You're in Australia. Go wake him up. I know you know him because you guys all live in like one spot, so you all know each other there. Go wake him up. Tell him to watch. Tell him we miss him. Okay. Yeah. So glad. Yeah, Anton's like killing it. So I mean, he's doing it. So he does it every day too. He posts something every single day.
Yeah.
So I'm not gonna do that. I don't care.
Well, he
Ain't
he
no
had
way I'm doing that.
a week's holiday last week,
Yeah. Well,
so he just put up compilations.
yeah, I'm just not doing that.
3-hour long
Yeah. I'm not
bits of education.
Yeah, he feeds that algorithm. He knows how to feed that algorithm. I'm not
Oh
gonna feed it.
yeah.
So, all right, guys, I'm out of here. Peter, thanks for joining. I'll see you guys back on
Thank
Thursday.
you.
We will talk about the Vera Rubin telescope. I almost said
Yes.
space telescope, and we'll talk about what it's doing. And if you got any questions or comments, and by all means, join the Discord server, A Deep Astronomy, because that's where the community really is. It's not on YouTube, it's not on Facebook. I don't even look at these anymore. I just stream there. And if you want to actually communicate, get on Discord. That's the best place for all of us because I love it there. All right. So thank you, Peter, and I will see you guys later. Thank you all so much for watching, and as always, keep looking up.
Good night.